Another factor that affects the stability of a charge is something called resonance. And resonance is very, very important for us. And we will use resonance to explain a lot of things. So this is super common. What is resonance? Resonance is a way of delocalizing charge What the heck is delocalizing charge? Well, delocalizing charge means spreading charge out. And so we're going to think of a molecule that has a charge on a certain atom, and we're going to draw alternative pictures that will show the charges on other atoms. So that's delocalization, that charge is spread out. Delocalization of charge through pi bonds and p orbitals. So we're only going to use resonance when we have atoms that have pi bonds and p orbitals, and that means we need to understand hybridization, because hybridization is where we learn to identify what orbitals an atom has. Does it have any p orbitals? Does it have any pi bonds? So this is now, hybridization ties very closely in with resonance. There are three different ways, three patterns for resonance. There might be others, but if there's 4 and 5, they're super uncommon. So 3 patterns for resonance. In this video, we're going to see just one of them. And in the subsequent video, we'll see the other 2. So a very common pattern, the most common pattern, so let's just number this number 1. We're only going to see number 1 in this video, is where we have an atom that's double bonded to another atom, and these are completely arbitrary. Atom A, I'm not trying to write boron here, that's simply some random atom. And you have 2 atoms double bonded together, and of course, what is a double bond? A double bond is a pi bond, so both these atoms have at least the features that we need, and they are attached to another atom that has a lone pair. In this case, we can spread out, we can delocalize charge, and maybe the better way to say this, instead of delocalizing charge, we're going to delocalize electron density. And since electrons are charged, technically we are delocalizing charge, but we're going to spread out electron density. So what does this look like? Well, we're going to do resonance, and we're going to move electrons around. So we're going to create alternative Lewis structures for this particular molecule, whatever it is that we've drawn. So to indicate that we're doing resonance, we use this arrow. This is our resonance arrow. It's not a chemical reaction arrow. Resonance arrow has arrows on both ends of the shaft of the arrow. And what we're going to do is we're going to move electrons. Anytime we move electrons by starting our arrows where the electrons are. So we're going to take this area of high electron density, this C atom with its lone pair, and we're going to use that lone pair to make a new bonding pair. Well, now the B atom has a problem. If the B atom had a full octet, it can't simply make a new bond. It would violate the octet rule. So as we make a new bond to the B atom, we're going to have to break an old bond to the B atom, and that's going to push those electrons, that pi bond, it's going to break the pi bond and put them up on atom A. And this is what we will end up with. We've simply moved the double bond, and the A atom will now have picked up an extra lone pair. If you go through your formal charge counting, which is very odd to ask when you don't even know the identity of the atom, but if the C atom started as neutral, it's going to end up with a positive charge over here. And the A atom has picked up a lone pair from a bonding pair, and so it's going to have a negative charge. And so this is delocalized electron density. The electron density has spread out, and we've drawn an alternate resonance form. Now, which one of these Lewis structures is more stable? Well, personally, I think this one's better, Because what are the rules of Lewis dot structures? Try to minimize the number of formal charges you have. And the structure on the left has fewer formal charges. Therefore, it's better. The structure on the right, though, is still a valid Lewis structure. At least it's going to satisfy the octet rule and all these other things. So what we say is between these structures aren't equal. One is better. One is the major resonance form. But this one on the right is going to have some explanation of the reactivity. So it's a minor contributor to the overall picture of this molecule. Now, these structures don't alternate back and forth. They exist together in real time. Another faculty member at Davidson used to talk about like a Cocker Spaniel Poodle mix. You don't have a dog that a cockapoo doesn't wake up some days as a poodle and some other days as a Cocker Spaniel. It is a blend of those two. In the same way, this molecule is a blend of both of these structures. It's mostly the one on the left because it's the major, and a small amount of the one on the right. But this is a way to visualize structures, and we'll see how these resonance forms are used to explain reactivity as we get more and more into acid-base chemistry.